This podcast is an intro to 3D technology using the MakerBot Replicator 2X 3D printer. I am Dr. Juana Mendenhall, and I am Associate Professor of Chemistry at Morehouse College. At the end of this podcast, you will learn several things. One is to understand what 3D printing technology is. Two, understand how 3D printing technology works. Three, learn terminology about 3D printing. And lastly, learn about the MakerBot 3D printing technology and some 3D design. We'll start out talking about the history of 3D printing and how it came about. 3D printing was a technology that was created in 1983 for industry to help improve manufacturing, but it turned out to be very expensive. It started out using large machines in large rooms that took up a lot of space and ultimately a lot of time. There was also technology that was used for inkjet cartridges that started out being able to print things in 3 dimensions using certain printer cartridges. Today, this technology has been coined the name additive manufacturing technology, or AMT. AMT is simply taking all of the previous known technologies and incorporating them into building thin layers one at a time that essentially print in 3 dimensions along the X, Y, and Z coordinate planes. Ultimately, they form the 3D structures that we know and see as a 3D printed prototype or mold. But given the history of 3D printing, what actually is 3D printing and how has the technology derived from AMT to actually being able to print on a smaller machine that's not in a large room and that can actually sit on a desktop? Well, 3D printing is the process of taking a digital model and making it a physical model. And typically we use plastics when we do this. It allows you again to create 3D structures by printing them along an X, Y, and Z plane, similar to what we learned in math class. We use various plastics to extrude, which means heat up and push through under pressure, a very fine nozzle that has a small orifice that then aligns each thin layer in 3 dimensions. The layers print one layer at a time until they fuse into one full model. That being said, for 3D printing, you can typically print anything you imagine. And if you imagine it, it's just a matter of time before you can actually create it on your own using all the tools that are available to you in the 3D printing world. Now that we have a better understanding of 3D printing, we want to briefly discuss the types of 3D printing technology that are currently available. There are several types of 3D printing technology available to date. However, each one is dependent on the user's need and the application that the user is after. So I'll briefly touch on each one, but the last one, or the latter one, is the one that we will ideally focus on for the sake of using the MakerBot Replicator 2X. The first technology we will discuss is SLA, or stereolithography, which is a laser curing or hardening of a liquid plastic that is used to build 3-dimensional shapes. There's also SLS, which is selective laser sintering. It's similar to stereolithography in the sense that it uses a laser, but it fuses powder instead of a liquid plastic. There's also layered object molding that again uses a laser as well, but it's used to cut paper one layer at a time into the preferred 3-dimensional shape. And lastly, the 3D technology that is employed in the MakerBot systems is called a fused deposition modeling. FDM is designed to basically melt or thread plastic through a metal nozzle that has a small orifice and that is attached to a movable motor. This motor, again, is designed to create three-dimensional structures by essentially lining everything up in the X, Y, and Z plane. So now we'll go into a brief introduction of the different types of 3D technology used and just tell you an overview of them all so you can have a comparison vantage point to see the difference in them. The first one we'll talk about is SLA, which is again our stereolithography. It's one of the earliest 3D methods developed, and it's based on using UV light to basically initiate molecules to link together and form three-dimensional plastics. This type of 3D technology or 3D printing technology is also known as rapid prototyping, and ideally using this type of technology gave great resolution and provided a lot of interesting structures for making circuit boards and things of that nature. In comparison to SLA, if we look at SLS, we're not talking about using things in a liquid form or doing things in a liquid bath. We are actually doing things with solids for SLS. So SLS also brings into play looking or working with solids or powders such as metals or glass or ceramics, and also using lasers to cut them into three-dimensional shapes or the acquired three-dimensional shapes that one would want at various resolutions. To compare these, SLA provided very good resolutions at its date and time. SLS was pretty good as well, but it required, again, large machines and a large system, especially working with metals and glass, things that would have to work at high pressure or under vacuum conditions. But lastly, we wanted to also look at the laminated object molding technology and how does this technology differ from the previous ones. Next, we want to talk about laminated object modeling, or LOM, which is also another form of 3D printing technology. LOM is also considered a rapid prototyping sequence that allows layers or blocks of paper, plastic, or metal to be cut with the laser. In the LOM setup, it actually uses rollers or moving platforms and lasers to cut and deposit new materials into the desired 3D shape. LOM is also used for more intricate type of 3D printing that require lower resolution structures, but again, these are more so for larger manufacturing systems. The next type of 3D printing technology that we will discuss is fused deposition modeling, or FDM. FDM is one of the most versatile 3D methods that can be used with many types of materials. We can use materials that essentially dissolve in water or plastics that melt at high temperatures. FDM also requires a motor to help it move in the X, Y, and Z directions. And MakerBot makes machines that use the FDM modeling technology that basically start around $1,500. And these are ideally for the small type of printers. So how does FDM work in 3D printing? FDM uses a nozzle of some sort that at the end of the nozzle has a small metal orifice that pushes melted plastic through. Once this starts to push through, we can then create substrates at various positions of different thicknesses, building it all within the XYZ plane. So now we're going to briefly discuss FDM and also define some key terms that are needed to learn more about 3D printing. One of the terms that we want to focus on again is FDM. This is employed in MakerBot, the technology that the MakerBot tools use. So if we look at the schematic above, the black portion is depicting the extruder head of where the plastic filament actually comes out. As this comes out, if you look at the bottom part, there's a blue line that's coming from the nozzle that is actually injecting the melted plastic. This essentially starts to build up over time onto a controllable movable table, which is defined later as a build plate. So, as we start to build 3D structures using FDM, using MakerBot 3D printers, there's also a term called slicing. Slicing is basically the term used to make a 3D model into thin layers. Filament is a word that is used to describe the plastic material, and it is basically plastic that is rolled on a spool that is attached to the back of the 3D printer that feeds inside of the black nozzle depicted in the schematic above. The extruder is the pointy orifice or the nozzle that you see located on the schematic above that has the hot metal tip and the small orifice hole where the filament or the plastic is actually being pushed through and deposited onto the movable plate. The movable plate is now called the build plate, and it's basically the surface where your 3D print will print at or build from. Build plates are designed either to heat, depending on the type of 3D printer you have, and in the MakerBot Replicator 2X, we have a heated build plate that allows us to print different types of plastics and experiment heavily with new things that could lead to more innovation here at Morehouse College. The build plate can also be not heated, that could be used for other type of materials. Typically the filaments that we use for 3D printing, the plastic filaments are ABS, acrylonitrile butadiene styrene, or PLA, which is polylactic acid. There's also different types of nylon and rubbers, and more recently some clay mixtures that have been developed to help with more sculpturing or designing busts for more artistic type of projects. So given the context of discussing 3D printing, 3D technology, and its purpose, I'm going to provide a different comparative analysis regarding the economics of 3D printing and how it works in the big scheme of things, especially when we use FDM. So there's an 80-20 rule that discusses or talks about the approximate use of the right material that will ideally enable a new generation of desktop printers to handle many of the same state-of-the-art applications that industry did years ago. And it provides a tremendous decrease in cost. So there has been a benefit from actually scaling down the industrial or commercial size 3D printing, additive manufacturing type of models to actually making them smaller, and it has created a global effect on the industry and how we actually look at innovating new things and 3D printing new things that has turned into this new area of makers. And as you know, we also have a makerspace at Morehouse that allows us to actually build upon these changes in the economics of 3D printing and ideally use with what most desktop 3D printers use is the FDM technology. Now that we know a little bit more about the 80-20 rule, I want to expand on just the global picture of the economics of 3D printing. Yes, we save money from the more industrial, large-scale manufacturing work, but it still has an economic impact due to the total cost of the parts that are needed, making the prototypes, the production costs, and basically the tooling maintenance, what we have to do to keep the tool running effectively. These parts can range from $50 to $500. So it's very imperative that we keep in mind that the economics of 3D printing, although we're creating three-dimensional structures for a less a lesser price or cheaper price than we did at the manufacturing facilities, ultimately these tools do cost money, and if things are damaged, it could cost a lot to repair those in the long run. Knowing that we can save money by using FDM and the MakerBot 3D printers or desktop 3D printers now, what are some of the applications that we can use 3D printing for, given the type of materials that are currently available to us? So now I want to just touch on a few things and the connection of how the filaments play a role in ideally making your prototype or the design that you may want to do. So traditionally, we can use our conceptual prototyping can use filaments such as PLA, which is polylactic acid, or ABS or nylon. When we actually want to make a working prototype, depending on what the application is, we can still continue to use ABS, nylon, perhaps some rubber, or new materials that are constantly being developed to be used in 3D printing. For some other production parts for wheels or other type of fixtures, there's always new materials that are constantly being evaluated and produced to provide better structures or more optimum structure for 3D printing. Now that we know a little bit more about what 3D printing is, the type of technologies that are used for 3D printing, the benefits of 3D printing, and also the types of applications and filaments we can use for 3D printing, I want to focus more now on how it is beneficial or can be beneficial to doing this in the classroom or for educational purposes. What I have compiled here is a list of 10 ways that 3D printing can be used in education, or it can be incorporated into curriculum. So first we'll start off with one of the obvious. Although we don't have an engineering school, it can still be used for research design projects or engineering design projects for students to make prototypes. There's also an advantage for students that could be interested in architecture that can also create 3D models of their designs. Believe it or not, history can also be used to print out historical artifacts or something used for some type of examination or archaeology or certain things of that nature. For our art classes or students that are interested in graphic design, we can also use some of their artwork, import things from Photoshop, and take a two-dimensional file and create it into a three-dimensional file. Students that are interested in geography, that could be taking a module in a particular course learning about geography. We can also use that to our advantage and 3D print things that talk about topography or demographic information or even spatial distribution of climate change. Students that could be interested in cooking, which is more so home ec type of things, but it could still be employed to actually making food products. We also do that in the laboratory as well, where we can 3D print icing into certain type of shapes because it is a soft material. Chemistry students currently at Morehouse College have printed 3D models of various molecules. Biology students can also print out cells, viruses, proteins, other biological artifacts. We also had students in the chemistry course print out certain enzymes that they were interested in. And it wasn't as difficult as one may see because there is a whole community of makers out there that share their creative production online. Some to the obvious, to link with engineering, mathematics students can also print out various components. We had summer students print out unit cells that actually drafted their own and designed it, and we actually 3D printed that last summer with high school and middle school students. And lastly, we begin to splurge or look into or merge into the business department where students were 3D printing prototypes that they wanted to ideally market or sell to investors. So there are always evolving ways to engage students into 3D printing and using 3D technology in the classroom, and we can easily start to move and incorporate this into the curriculum. So now I want to switch gears a little bit and moving to actually talking a little bit more about 3D printing and the tangible aspect of it. So we can easily make printable parts, but unfortunately, if we don't set up properly, make sure everything is aligned properly, calibrate the tool properly, we can put garbage in with a bad 3D design and we can get garbage out. So the image above depicts a bad 3D print, and it happens more than you would think because we always have to be mindful of what our design is and is it formatted properly and is the printer ready to receive it. In addition to that, we want to move into telling you more about what the online 3D community is about. It's licensed under a Creative Commons agreement where other makers or innovators can post things that they have made, and they will actually give you the 3D file that can be used. So typical portals that one or users go to, the first one, which is very popular, and it is affiliated with MakerBot, is Thingiverse. Thingiverse is a very open portal for searching for 3D prints. You can just enter into the search bar whatever you're interested in and see if anything comes up. Believe it or not, there are so many things out there. There are also other tools that can help you to actually design 3D models that may not be available on Thingiverse or other portals. Several websites or software packages that we use include PrintShop, 123D Design, and Mesh Mixer are used for creating any type of design you want. It's very user friendly, and we've had several students at Morehouse that actually prefer to use 123 Design. So that is the one that I recommend as well. We also have Tinkercad, which is also a very user-friendly one, and I've also had high school and middle school students work with Tinkercad, and the learning curve is not as steep. OpenSCAD, which means just a computer-aided diagram, which is what CAD stands for, is also used to help you create 3D design. Sculptris, it focuses more for the artistic graphic designer, and Google SketchUp is very technical, high learning curve, not recommended unless it's for architectural work. Blender is another option that also uses more animated type of designs, animation type of cartoons. It's very sophisticated. So the more user-friendly 3D printing online portals that I recommend are Thingiverse, 123 Design, and Meshmaker, and Tinkercad. But of course, you're always welcome to play around and see what works best for you and your students. Next, I want to touch briefly on how do we go about making a 3D printable design file. I want to provide some background on what the 3D design files are and what's the typical terminology used. However, this will be an overview. I will go more into this in another podcast and using an lecture style format. The standard 3D printing format extension is called an STL. An STL file is typically generated from a computer-aided manufacturing type of design. This is basically the file name for softwares that actually allow you to design things in 3 dimension. When these type of designs are created in the software programs that I mentioned previously, 123D Design, Google SketchUp, Tinkercad, they will have the file extension of STL. It's important to know that once we create these files, they are then sliced up in 3 dimensions to be exported into either an STL file, or an X3G file, which is noticed by the MakerBot. STL files are also recognized by MakerBot, but the typical MakerBot printer prefers its files in the X3G format. Again, there will be other podcasts and lecture style formats to further show the differences in how we can actually go about manually creating 3D files. Another option is to look at the actual MakerBot software and what it looks like as far as working with 3D files. In the image above, this is the software program called MakeAware that's used to 3D print. And as you can see, for our mathematics instructors, this is a mathematical structure, a polyhedron or a tetrahedron that can actually be created and drawn using 3D design. We would simply just export this into the appropriate file extension that could be later transferred to the 3D printer. There are also websites that allow you to also transform your STL file or your CAD file into the right extension, and that is also called 3dtransform.com. Given that we know a little bit more now about the type of 3D printable design files we can make, software that we can use to actually make 3D models, and some of the terminology that's used to create the 3D models or the tangible form of the 3D print, I also want to provide some guidelines for a successful desktop 3D printing using the MakerBot Replicator 2X. As stated before, the MakerBot Replicator 2X 3D printer is used with FDM technology, and it's an experimental 3D printer, which means it's the ideal printer that is used to create innovative things, and there's a lot of wiggle room to play around with new type of prints, and we can really push the limits using the MakerBot Replicator 2X. So some helpful tips that ideally I wanted to share when it comes to successfully 3D printing. It's the first one that we want to make sure that our CAD file, computer aided design, or is a STL file is accurate. It has to be watertight, meaning that it doesn't have any flaws in the dimensions. It has to be on the actual grid that represents the bed plate, so it has to be very accurate. Again, we'll go more into that on the second podcast. But you need to make sure that everything is calibrated appropriately. So calibrate, calibrate, calibrate. This will be shown more with the hands-on component of learning how to 3D print, but calibration, we want to ideally make sure that the bed plate is calibrated, our nozzles are calibrated, and everything is all set ready to go. We have to make sure that we choose the correct filament. The filament for the type of prototype of print we want to do. Given it could be ABS, PLA, or some other type of mixture of plastics that we want to use. We need to verify the print head and the print speed. What that means is that the print is actually working appropriately with what it is trying to print. We could print it slower or faster, and that will control the type of resolution and detail we will get in the ultimate print. Printing temperatures are extremely important because this is dependent on the type of filament that we are using. The type of filaments we use is geared towards the printing temperatures. If we do not have the right printing temperatures, the filament or the plastics will not dissolve or melt appropriately. So we need to really hone in on that and make sure that we have the right temperatures set in the program, which we do in the MakerAware software. We also need to make sure that we have cooling fans working and they are working to their optimum efficiency. If there is a fill-in strategy used for printing the structures, we'll talk more about that when we learn more about the software. We need to make sure that that is accurate as well and it's holding the 3D print or the 3D mold together. For the bed plate, there's a lot of things that happen when we print on the bed plate that could allow the print to shift and move and not stick or be adherent. Hence, we need to make sure that the temperature is set appropriately and that the print will actually stay connected to the bed plate and not move. If this happens, then we won't have a successful print. Again, make sure we have the right material for our application. Make sure the environment is controlled, the temperatures are ambient around it, and nothing is too hot or too cold, and that the design is going to fit on our bed plate. This ideally is created when you actually work in the 3D design software. Common problems with 3D printing that we have to be mindful of are listed below. So in advance, I like to always recommend that we triple check what we're doing with the 3D printer. And it does happen because this is an experimental procedure. Sometimes things do not go as planned every time. So we have to have patience with the process. The first thing that we can always double check is that our CAD design or our ST file is not flawed or not defective. So those are the key components. We start with our design first. Number 3, which I've underlined because it is very important, we want to make sure we have the proper calibration. If we have poor calibration, this can cause a problem with the ultimate print when it actually happens. We also need to confirm that we're using the right filament and that we have the correct printing temperature set for that filament. We also want to double check the printer settings. Do we have it printing at high resolution, low resolution, or normal resolution? That again, depending on the resolution we want or the details of the structure, how intricate we want it, we want to make sure that everything is in a line so that there will not be any problems. We also want to verify the temperatures in the room and the ambient conditions to make sure that the room isn't too hot or too cold. Therefore, the 3D printer can remain stable and it doesn't overheat and cause problems in the actual print itself. And lastly, we want to make sure, as I stated before, that we triple check our bed plate and the adhesion component on the bed plate. So this also means if we want the bed plate to be heated, that is also checked and recognized in the software. And we want to make sure that whatever we print on, it will allow the print to actually stick to the bed plate. Things that we use to help with bed plate adhesion are things such as blue painter's tape, double-sided tape, and there's also Kapton tape, which will be supplied when you actually do your 3D printing. So there are several variables that we need to keep in mind when we're starting the print that, this isn't an exact procedure or an exact science, that we'll have to kind of go back and always triple, double, quadruple check ourselves to make sure that everything is in a line to get a successful print. In addition to the poor bed plate adhesion, there's also issues that can occur with the extruder nozzles. So the other option is to make sure that the heating is going properly and that your calibration lines are actually extruding properly. Typically, if there is a clog in the extruder, you will be asked to contact one of the lead trainers on the tool to make sure that they can unclog the extruder nozzle. It does happen, and it ideally happens when there is not enough plastic or the temperature is not appropriate for the plastic or the filament that you are using to do your 3D print. As a reminder, when making functional prototypes, we want to keep several things in mind. Recall that we want to make sure that our CAD file, STL file, or X3G file, it is meeting the proper specs or specifications needed. You need to be extremely careful when you take something small and try and scale it up. There could be issues with warping, shrinkage, moisture absorption happening depending on what type of filament or plastic you are using. Keep in mind that there is a physical component to this first, which means we have to make sure that the temperatures and things like that are appropriate, and then the aesthetics come second. Recall, if we put garbage in, we can get garbage out. So we need to always triple, double check what we're working with prior to actually starting the print. Say you have a student or there's a project where we want to make functional prototypes and we need to make several components. The beauty of 3D printing is that we can design multiple parts and ultimately combine them together for the final result. In the slide above, You can note that there are ways that we can produce robotic hands, bicycles, and either other small components where we have to screw them together. Keep in mind, we have to remember that we want to balance the physical aspect of this, the design portion, with the aesthetic character so that everything will work in tandem together to create the effective 3D model that we ultimately want. There are a few key points I want to bring to your attention regarding the implementation of 3D technology into the classroom or into curriculum. One is that you always have to be patient with the printing. It can take some time to get the best print. It can be trial and error. We have to always triple check things from beginning to end. We also have to make sure that we're using the proper material for the specified application, be it conceptual prototypes, functional prototypes, or things on a small scale. There are also custom parts we can make using other type of filaments that dissolve. We can continue to design various new models to print, and we can also use 3D technology and 3D printing for research and development. Lastly, there are always new materials that are constantly being developed and used that can also expand what we are currently doing in the field of 3D printing and 3D technology. So, just to reiterate, the 10 ways that we can incorporate 3D technology and 3D printing into curriculum and into education is that again, we can focus on our students in business and econ, our mathematics students by solving a mathematical problem or drawing infrastructural designs. We can use this for our biology students where they again are looking at some protein functions. We can 3D print hearts, we can 3D print livers with filaments and non-filaments. Chemistry students are doing a lot with molecules. We can move into more three-dimensional molecular structures as well. Our geography students that are interested in topography and demographic information or using some type of computer science spatially populated design we can actually work with. In art education, we can employ with trying to do some graphic design work and creating designs again from two-dimensional structures and making them into 3D versions. History, we can do some artifact work. And again, for research and design projects for architecture or engineering or dual degree students, there is an opportunity to actually really engage students and faculty into 3D technology and incorporate it into our curriculum. And it's easier today than it has ever been. In summary, this podcast was designed to introduce you to 3D printing technology and provide you with the context of the history of how 3D technology has evolved, the types of 3D printing technology used, the type of 3D printing technology used with the MakerBot Replicator 2X, give you an introduction to 3D design software that is used to create 3D images, and also inform you of the Creative Commons websites that are used for sharing 3D design files. I also wanted to provide some context on the type of materials that are available to be used for 3D printing, and more importantly, I wanted you to learn what the material could be for an intended application and how you can incorporate 3D printing technology into your syllabus for various classrooms around the college. You can learn more about 3D printing technology by looking at podcasts on my YouTube channel under Morehouse 3D Technology and also Blackboard through the Faculty Development Center.